Abstract. Agriculture plays a crucial role in developing countries, such as Vietnam, where 70% of the population is employed in agriculture, and 57% of the social labor force works in the agricultural sector. Therefore, crop productivity directly affects the lives of many people. One of the primary reasons for reduced crop yields is plant leaf diseases caused by bacteria, fungi, and viruses. Hence, there is a need for a method to help farmers identify leaf diseases early to take appropriate action to protect crops and shift to smart agricultural production. This paper proposes lightweight deep learning models combined with a support vector machine with hyperparameters fine-tuned by chemical reaction optimization for detecting plant leaf diseases. The main advantage of the method is the simplicity of the architecture and optimization of the DL model's hyperparameters, making it easily deployable on low hardware devices. To test the performance of the proposed method, experiments are performed on the PlantVillage dataset using Python. The superiority of the proposed method over the well-known VG16 and MobileNet V2 models is demonstrated by a 10% increase in accuracy prediction and a decrease of 5% and 66% in training time, respectively. Main contributions of this article are proposing a lightweight deep learning model that can easily be deployed on low hardware devices, replace the last layer of convolution neural networks with support vector machine to improve classification accuracy prediction, optimization of hyperparameters of the deep learning, and support vector machine model. Introduction. The 2023 Global Report on Food Crises shows that there is a growing need for food and livelihood assistance. The report reveals that over 250 million individuals are faced with acute hunger. In 2022, the count of individuals experiencing severe food insecurity at crisis or more severe levels reached 258 million across 58 countries and territories, a notable increase from 193 million individuals in 53 countries and territories in 2021. One of the primary reasons for reduced crop yields is plant leaf diseases caused by bacteria, fungi, and viruses. Because plant leaf diseases often affect the chlorophyll content and structure of leaves, which are crucial for photosynthesis. Reduced photosynthesis leads to a decrease in the V, ultimately affecting its growth and yield. In addition, many leaf diseases cause symptoms such as necrosis, wilting, or premature death of leaves. This results in a reduction of the total leaf area available for photosynthesis. The loss of leaves can significantly impact the plant's ability to capture sunlight and convert it into energy. Therefore, protecting crops and increasing crop productivity is an extremely important task. Currently in Vietnam, the widespread use of pesticides leads to affecting the health of farmers, polluting land and water sources, and reducing the quality of agricultural products. In addition, the evolution of climate change is very complicated, leading to increasingly serious diseases related to plant leaves. In particular, diseases on crop leaves are very common and seriously affect crop productivity. Recently, researchers have used machine learning and deep learning models to classify plant leaf diseases. However, almost all researchers have employed the complex architecture of CNNs, which involve a large number of parameters. Consequently, previously proposed solutions are challenging to implement on hardware with limited performance, such as mobile and IoT devices. Additionally, the hyperparameters of CNNs are often chosen based on experience, making it difficult to achieve optimal models. In this study, a lightweight CNN model is designed for easy integration into low-performance hardware devices and high-accuracy prediction. In addition, a novel method that utilizes the chemical reaction optimization algorithm to optimize the tunable parameters of the CNN and SVM model is introduced. Furthermore, to enhance classification accuracy, the last layer of the trained CNN is replaced by an SVM model. Initially, Images depicting plant leaf diseases extracted from the PlantVillage dataset are employed to train and evaluate the proposed deep learning model. Subsequently, the final layer of the trained DL model is substituted with an SVM for enhanced classification accuracy. The hyperparameters of both the DL and SVM models are fine-tuned using the CRO algorithm. Methodology. Convolution neural networks. The structure of the deep learning network illustrated in Figure 1 includes convolutional, pooling, and fully connected layers. As the CNN progresses through its layers, its complexity grows, allowing it to detect larger areas of the image. The initial layers concentrate on basic characteristics such as colors and edges, gradually advancing to recognize more substantial elements or shapes of the object. Ultimately, the CNN reaches a point where it successfully identifies the intended object. The convolutional layers serve as removing noise and boundary detectors, whereas the pooling layers perform computations to obtain either average or maximum local values. Reducing the size of the image, fully connected layers perform classification tasks. The convolutional layer performs a summarization of the element-wise product of two matrices. The first matrix represents a portion of the input, while the second matrix corresponds to the kernel. Figure 2 illustrates the calculation process of the convolutional layer. The pooling calculation is illustrated in Figure 3, where the stride determines how quickly the kernel moves both horizontally and vertically across the pixels of the input image during convolution and pooling. SVM. Support vector machines are widely utilized in the domain of machine learning for classification purposes. SVM aims to find the optimal hyperplane that effectively separates data into two categories, with the margin representing the maximum distance between the hyperplane and the closest sample. Figure 4 illustrates a hyperplane along with its associated margin. Hyperparameter optimization formulation. During the design phase of machine learning models, efficient exploration of the hyperparameter space through optimization techniques can identify the optimal hyperparameters for these models. HBO comprises 4 essential components: an estimator comprising its objective function, a search space, a search algorithm used to uncover tuning parameters, and a scoring function for comparing the effectiveness of various tuning parameter setups. Typically, the goal of the HBO problem is to pinpoint a specific point within the search space. For deep learning models, the search space can include the number and size of filters in the convolutional layers, the activation function, the neuron count within the fully connected layer, and the initial learning rate. Suppose we need to find an optimal tuning parameters for a deep learning model. Each tuning parameter has a discrete or categorical value domain with several options MI and the corresponding search space SI. The CRO algorithm is a contemporary random search employed for the problem of optimization, mimicking the dynamics of loosely coupled chemical transformations within optimization processes. In a chemical reaction system, various chemical substances interact within their environment, each possessing both potential and kinetic energies, while the environment itself is represented by a central energy buffer. As a chemical reaction reaches equilibrium, all substances stabilize with minimal potential energy. CRO emulates this equilibrium process by transforming potential energy into kinetic energy, slowly discharging the energy stored in chemical molecules into the surroundings. CRO is founded upon 4 basic transforms: on-wall ineffective collision decomposition, intermolecular ineffective collision, and synthesis. While 2 ineffective collisions facilitate local searches, the others facilitate global searches. Consequently, CRO effectively integrates these 2 search types to explore the global minimum within the feasible region. by amalgamating the beneficial aspects of both simulated annealing and genetic algorithm. CRO maintains energy conservation akin to the Metropolis algorithm used in SA, while its decomposition and synthesis operations resemble the crossover and mutation operations of GA and CRO. Every molecule is defined by a molecular structure, serving as an answer to the issue, along with two types of energy, P and Ke. P corresponds to the value of the fitness function, while Ke denotes a molecule's tolerance to an increase in its energy state. To simulate four basic reactions based on three operators, neighbor, decomposition, and synthesis. The neighbor operator is used in the collision reaction to create a new solution from a particular one. The new solution is created by changing randomly selected elements in the current solution. The goal of this operator is to conduct a local exploration for a better solution. Proposed method. The principle of the proposed approach involves a combination of a deep learning network and an SVM model. The deep learning network is responsible for extracting features from images of diseased leaves, while the SVM serves as the classifier. Initially, images of diseased leaves are extracted from the PlantVillage database. Subsequently, these images are augmented by rotating them at specified angles. The augmented images then undergo feature extraction through the proposed lightweight CNN network. Finally, the image features are classified using the SVM model. The performance of deep learning networks mainly depends on their architecture and hyperparameters. In this paper, the CNN structure is designed to balance simplicity with the ability to extract all necessary features. This architecture is suitable to be deployed on devices with low hardware configurations, such as embedded computers or mobile phones. Additionally, the optimal tuning parameters for both the CNN network and SVM model are determined by using the CRO algorithm. The structure of the proposed model includes 5 convolutional layers and 2 fully connected layers, as illustrated in Figure 5 here. Key, me, phi, and n represent the number of filters, size of the filter, activation function, and the number of neurons, respectively. These are tuning parameters that require optimization. This dataset is highly renowned, encompassing more than 50,000 images, and has been extensively utilized by experts for plant disease diagnosis. The PlantVillage comprises 38 image classes depicting disease symptoms on leaves, and 1 image class without leaves. Due to hardware limitations, the authors restricted their experiment to using only 100 images per class. Some images of plant leaf diseases are illustrated in Figure 7. Details on the dataset used in the experiment are summarized in Table 1. Hyperparameters KI, MM, FIF, NN, CC, sigma, and kernel F are found by the CRO algorithm. CRO algorithm are set as pop size equals 10, K loss rate equals 0.1, mole call equals 0.1, initial K equals 100, delta equals 500, theta equals 10, and buffer equals 0. The suggested algorithm is implemented using Python programming language on Google Colab. The proposed DL is implemented by TensorFlow and Keras platform. The initial parameters of the CRO algorithm are set as pop size equals 10, K loss rate equals 0.1. The SMB model is implemented using the Sklearn framework. The authors implemented the CRO algorithm. The proposed CNN is trained using early stoping, reduce-LR on plateau, and the 5-fold CV techniques. The SVM model is trained using the 5-fold CV technique. The tuning parameters of the CNN model were found by running the CRO algorithm implemented by algorithm 5 are M1 equals M2 equals M3 equals M4 equals M5 equals 1. K1 equals 32, K2 equals 64, K3 equals 128, K4 equals 256, K5 equals 512, N equals 512. F1 equals F2 equals F3 equals F4 equals F5 equals F6 equals real U. This finding is reasonable because it is well suited to numerous deep learning frameworks and hardware accelerators, which are tailored for optimizing power of two dimensions. In addition, gradually increasing the number of filters and deeper layers enables the network to capture increasingly intricate